I should clarify when I say solving gravitational potential energy problems on the board. It's not just gravitational potential energy problems, but it's problems that involve kinetic and potential. Because as you rise, you gain potential, but you lose kinetic. And there's that idea, Steve, of conservation of energy. Okay? So that's the topic for the day, motion in the Earth's gravitational field from an energy standpoint. We did in grade 11, we solved problems that were rising. In the projectile motions unit, we solved problems where the projectile was going at an angle and rising, and we've taken care of that. But we haven't looked at things from an energy standpoint. We have a little bit, but not so much in depth. So that's today's topic. And for some reason I was big into, I think this is an old PowerPoint that I converted to Smart Notebook, and I've never actually updated it. So you'll have to pardon the weird looking stuff. Again, as always, write what you feel you should. Write what you think is needed. And some of you just need better practice at prioritizing what is needed and what isn't. Okay, so work done in lifting a mass of vertical distance d or h is stored inside the body as increased potential energy, i.e. increased gravitational potential energy, UG or just plain old U. Why do we use U for potential energy? No idea. If you want to call it PE, potential energy, you go right ahead. If you want to call it EP for potential, go right ahead. If you want to call it EG for gravitational potential energy, go right ahead.
So will it ever show up as UG?
The stuff that I'm doing will show up as UG. Probably because some textbook where I was initially creating my set of notes probably used that and it's forgotten in the midst of time as to where I got it from. But you may see that in your future. Who knows? So you've seen this in the introductory discussions, introductory handouts as well. So I'm just reminding you that the work done is stored as gravitational potential energy. Okay? Since W is Fd, and the F is equal and opposite to Fw, which is mg, and D can become h for height, W equals Fd becomes U equals mgh. I just derived the formula. That's the formula there. U equals mgh because W is Fd, W is weight force D, so that's mgd, and we're going to call that mgh, and that's equal to the gravitational potential energy, mgh.
So this work is equal to that then, basically?
Well, the work that you do is the potential energy. Any work that you do gets, because energy must be conserved, right? So if I do 50 joules of work in lifting an object, it's got 50 joules of energy have to have gone somewhere. Oh yeah, we've got that already. Yeah. So we're going to solve for this, but we're going to solve for, because there's total energy, right? We're going to solve for both kind of thing. Okay, this is sort of the key sample, key idea here. So changes in ground potential energy and kinetic energy as the object moves in the Earth's gravitational field. So here I've got a 5 kilogram perfectly spherical snowball on top of an 8 meter high ledge. How much potential energy does it have? U equals mgh. 5 times 9.8 times 8 are 392 joules of gravitational energy. Is that big enough for you guys? Do I need to make it bigger? Does that make sense so far? It's sitting there. Where did that 392 joules come from? Don't know. That rock could have been sitting there for billions of years. We have no idea. Somewhere along the way, some work was done to put it there. How much kinetic energy does it have? Big fat 0. How come? Not moving. I ask an easy question. What is the total energy? 392. ET is kinetic energy plus potential. 0 plus 392. Total energy, ET, 392. Cool, that's just, we're just setting the groundwork here. Does the total energy have to remain the same throughout the period of motion. Like this ball here is going to fall off, and it's going to come hurtling towards the Earth. And as it does, it's going to pick up speed, which is measured in meters per second, I guess. And that's a way of showing kinetic energy, right? And as it gains kinetic energy, what does it have to do to its potential? Has to lose potential, right? In fact, as it gets to a spot right here, it's not near as high in the air, so it has less potential. And in fact, that's balanced by its kinetic energy. Okay, I think on the next slide here, I just rewrote that stuff. So you guys can just, I don't know if you're writing it or not, but you don't obviously need to write again. I just needed it all on the same screen, that's all. Okay, so now I'm at a point here, 3 meters in the air. How much potential energy does it have? 5 times 9.8 times 3, 100. I have 147 joules of potential energy. I've lost potential energy. Where did it go? It went into speed. It went into kinetic energy. How much kinetic energy does it have? Well, you could go back, way back to Unit 1. dF squared equals Vi squared plus 2AD. dF squared equals 0 plus 2 times 9.8 times 5. It's moving at 9.9 meters per second. And then we can take that and convert that to kinetic energy by doing that. And we find out that it's got 245 joules of kinetic energy.
We have that.
EK equals mv squared over 2?
Yeah.
You would have got it on Friday.
So that was,
That was Friday. Yeah. Yeah. You'll need to get that. I think I also gave a $20 bill to everyone and the answers to the exam on Friday.
Is EK kinetic energy?
EK is kinetic energy.
And it'll always be like a motion, like a current motion.
Yes, it has to be moving. It has to, if the velocity is 0, right, Jason?
Yeah.
The velocity here is 0, then the EK is going to be 0. Okay. So, some of you might have said, well, couldn't I have just taken 392 minus 147, would that give me 245? Absolutely. Is the total energy still 392? Yes, it is. 245 plus 140. So, I mean, like this is sort of the wrong way to do it. What you really should do is take 392 minus 147 and get the 245. The total energy must remain the same. Should I just pause there for a second? Let you soak that in? If you know this, if you did it this way, if you went 392 minus 147 and got the 245, could you then work backwards to find out how fast it was going? And would you get 9.9? Of course you would, right? Because you'd have 245 here and you'd know the mass, you'd easily get 9.9. It all works together. Okay, that's all that on the same page again, right? I've just got it there to visualize. Delta U, I'm sort of putting it all together here now. Delta U, change in potential energy, is final minus initial. Final was 147, initial was 392. My change in potential energy, minus 245. I lost 245 joules of potential energy. How much kinetic energy did I change by? Plus 245. Right? Delta EK is EKF minus EKI, 245 minus 0. So I lost 245 of potential, I gained 245 of kinetic. Conservation of energy.
So they should equal out or something?
They should equal out perfectly, right? Now, in the real world, are they going to be perfectly equal? No. There's always a little bit of energy lost, usually in the form of heat or light or sound. Generally heat. Right? If something's falling through the air, is it going to heat up? When the space shuttle went boom, was it heating up? When anything re-enters orbit, does it heat up? Yes, it's traveling at a very high speed. It enters the Earth's atmosphere, where it encounters a huge amount of air resistance, and it heats up. That's how it slows it down. It's losing kinetic energy in the form of heat. And the heat tiles have to sort of protect the inside of the spacecraft. Note that total energy is the same at all times. And as an object moves, the changes in potential and kinetic energy are equal and opposite. Am I good? Yeah, all makes sense? I've sort of been repeating myself here. I feel like I've been repeating myself. If you feel like I've been repeating myself, then you get it. I don't know how I ended up with the question with Rocky the flying squirrel. He's not actually a flying squirrel, he's a gliding squirrel. Squirrels don't fly. Okay, so, and it was always, yeah, Bullwinkle was always the one driving off that high diving board into the thimble of water, too. Okay, Rocky the 1 kilogram flying squirrel initially up to 10 meters in a tree, then he jumps down to the ground, find the total energy at the start, which is the total energy at all times, and his velocity after he's fallen 6 meters. In other words, he's 4 meters from the ground. So, total energy at the start, U equals mgh, 1, 9.8, height of 10. Look at how easy that is. He has 98 joules of potential energy. Just today I had my grade 11 class. We went outside because it was so hot here. And they wanted to know how fast they'd be going if they climbed a tree and fell 5 meters. So this is how I figured it out. People worked out to about 80 kilometers an hour. That seemed a little high. We'll see here. This guy's 10 meters up in the tree, so we'll see what this works out to. So what is his velocity after he's fallen 6 meters or he's 4 meters from the ground? How would you like to attack the next?
The total energy is the potential energy?
Yeah. ET then is 98. He hasn't jumped yet at the start, and not an A,
Oh,
right? So his total energy is 98. So could we figure out a couple ways to do this? The way I like to show people is find the potential energy. I'm going to put U4. What do you think that means?
4 meters from the ground.
Yeah, at 4 meters from the ground, right? So here we're going to have mgh 1, 9.8 times 4, 39.2.
How come we don't do it by 6?
He's fallen 6 meters. That means he's 4 meters from the ground, right? So he's got 4 meters of height. Total energy is potential plus kinetic. Total is 98. Potential 39.2. Let's find how much kinetic energy this guy's got. 58.8. And that kinetic energy is expressed in terms of a speed.
that's an 8.8?
58.8, yep.
Wait, so couldn't you just take the complete opposite? Couldn't you just do times it by 6 meters for what he's fallen, and that's what
Yeah.
you find the kinetic?
What do you mean by times what by 6?
Your 9.8, because you went 1 times 9.8
Yeah,
for your weight force, whatever.
yeah.
And then if you times it by 6, you can find your kinetic energy instead of, because it's 58.8 is kinetic, right?
Yeah.
And I went 1 times 9.8 times 6, and it gave me that exact answer.
You got 50. Oh,
Because I times it by how much he's already fallen.
Yeah.
It gives me the kinetic energy.
well, if you go 1 times 9.8 times 6, you're really finding the potential at 6, really. They're always going to be opposite of each other. So because the 6 and 4 add up to 10, right? That's why the 39.2 and the 58.8 add up to 98. But
But if we had like 3 different.
yeah, you'd have to be careful. Yeah. Yeah. I'd be cautious doing that.
Yeah.
Okay, so mv squared over 2, 58.8. Mass is 1. Velocity squared over 2. So v is the square root. Take 58.8 times by 2 and take the square root. 10.8. Or about 39 kilometers an hour. Now, that's not even close to what I got this morning.
Wouldn't your mass have to do with it a lot though? Or no?
Yeah.
Is there mass to be?
Because like the mass for kids gonna be a lot heavier.
Yeah, you're right, but a good point, Steve, and that crossed my mind for a second too. But here we're including the mass, we're multiplying the mass in, and here you're dividing by the mass, right? So if I put like 10 in there, and then put 10 here, I end up multiplying by 10, and then dividing by 10. So it takes it out. Because remember, Galileo said it doesn't matter how big the object is, it's going just as fast at the bottom, right? So the mass doesn't matter, but the amount of energy matters. That's why you'd rather get hit by a falling tennis ball than a falling piano.
What about
They'd be traveling at the same speed, one would just have a lot more energy. What about what?
No, it's Stevie hit Luke with a tennis ball the other day.
Oh, really?
That spot.
Oh, ouch.
So,
Yeah?
Full swing. Okay.
Give this one a whirl. Notice that it's launched at ground level. We need to find the total initial energy and the height of rise using energy. So it's going up like this, and it's actually landing on a ledge partway up. Give that a little thought there. Yes, but like it's muzzle velocity. Launch velocity. I'll let you try. Okay, well,
It was a crash for, I think.
that's fine. That's okay. We'll learn from our
Yeah.
challenges. 2 kilogram balls launched at a ground level at 50 meters straight up, 50 meters per second. Find the total initial energy. So it's all at the bottom. It's all kinetic, right? EK is mv squared over 2. So it's all 2 times 50 squared all over 2, which is just 50 squared, which is? So 2,500 joules of kinetic energy at the start. Did you get that?
Yeah.
Okay, so that was a good start. Find the height of rise using energy. If it has 2,500 joules of kinetic energy at the start, at the end, when all of that energy is converted to potential, how much energy does it have? The same amount. No. It has 0 kinetic, but how much potential does it have? It has 2,500. All 2,500 became potential. And the mass is 2 and gravity is 9.8, and that means we can solve for h, which is going to be 2,500 divided by 2 times 9.8, 19.6, right? Hmm. 120, is that right? 127.6?
Yeah, sure.
Okay. It went a long ways up. What's its kinetic energy when it's risen halfway? Well, would it be half as much, do you think?
What is which one?
What is the kinetic energy when it's risen halfway? Well, halfway would be 127.6 divided by 2.
What's the H?
Height, 63.8. How do I find out the kinetic energy at that height? Give it to me in words. What steps? What do I have to do first, man, do you think? Don't know? Okay. Yeah? Find the potential at that height and then subtract from the total, exactly. So U equals mgh to 9.8, height of 63.8. Is that me?
Oh, is it?
Hmm. 1250.5. That's half, isn't it? Is that not half of 2500? I know what it is. I've got a button right here. That's why I think it's doing that. No, I'm not getting any sound at all.
Just turn it off, so it's like
Do you need me?
Oh,
Do you need it on?
Cool.
No? Okay, kinetic energy when it's risen halfway, so therefore, let's just for the sake of completeness, let's write ET, total energy, EK plus U, total is 2500, solve for kinetic, potential, we'll just say 1250. Right? How fast is it going when it's risen 100 meters off the ground? What do we have to do to find that last one? Exactly the same thing, right? Exactly the same steps. Do we even need to do that? The last part is not the halfway part, but velocity when it's risen 100 meters off the ground. So we're going to take, we don't even have to do this, right? We're just going to solve the potential at 100 and then subtract from the total. Do I even need to do that? Do you want me to? Do I have to find the velocity?
Yeah.
Oh, it says velocity? Oh, okay. So then what would be the last step? Yeah. No, just use kinetic energy, mv squared over 2. Let's do it. U equals mgh. 2 times 9.8 times 100. $1960? ET is equal to AK plus U. 2500 is equal to EK plus 1960. $540 joules of kinetic energy, and then what? mv squared over 2. $23.2. What do you think? Doable? Not terribly difficult. Just new. You're right. Just takes practice. You guys try number 3. Number 3 is exactly the same as 2D. Am I right so far?
I didn't get that one.
What?
Am I right so far?
I got way less.
No?
What'd you get?
Not in my eyes.
No, time to deal with it.
Okay, you guys are giving me a lot of
Wait, what, that?
confidence here.
68.9.
No, it's definitely 45.
3 times 9? Yeah, it's definitely 45.9.
Oh, I meant to put 2.
Yeah,
Which
so
counts there?
that's where it's at.
Big count.
Yeah, oh yeah. Recalculating route. Maybe I made that mistake on purpose to make you all feel good.
Oh, yeah, sure. Is that it?
Does it make you feel good that I made the mistake and you got it right? Maybe I just make the occasional mistake. Yeah, I'm not that good. It just worked out that way. Okay, so how fast is it going just as it lands on the ledge? So it goes crazy high up, and then it lands on this ledge that's 5 meters high in the air, right? So how am I going to do this? I'm going to find the potential energy at a height of 5. $147. Right? And now I got to find out how much kinetic is left over at that point. ET is equal to EK plus U. The total is that 1350 value. We're solving for kinetic. There's 147 of potential. I get 1203. Am I good?
I think most people just recalculated it with 40.9
Yeah.
instead of actually just minus it from the total.
Like, are we redid U as 3 times 9.8 times 40?
Oh, no, no.
Oh.
You found it at 5?
Yeah.
You just subtracted 5 and found it at 40.9. Instead of...
Subtracted 5 from the total distance.
Oh.
We came up with that same answer, just 0.5 different.
Yeah.
Huh. Okay. I'm not sure that the way you're telling me, I haven't seen it, but I'm not sure I like it.
I mean, instead of having a ledge of 5 meters, and
Yeah.
you just put it away from the total distance, it's 45.9
Yeah.
meters each.
So you put
And you reduce it by 5 meters to a 5-meter ledge.
Oh.
That's a random question.
Okay.
We got the same answer.
Okay. I'm trying to, I know you got the same answer, I'm trying to follow the logic, but I don't mind the way you explain it. You like my way? I like my way because I'm trying to reinforce the idea of that the energy is conserved. So, fair enough. So V is 2 times 1203 divided by 3, and then I'm taking the square root of all that. $28.3?
Yep.
Yeah.
Okay. All right, I will stop yakking. I think I handed out a problem sheet there. I made sure there was a QR code for you. We will do this. My notes tell me that I should do the spring lab before the actual notes, so let's plan on doing the spring lab tomorrow. It is not a full period. You can easily get the lab done in a 60-minute period very easily. So we get a little bit of time to work tomorrow. We'll do spring notes, which are it's probably one of the easier topics there is, on Wednesday, and I'll give you a day to wrap up on Thursday. And those people that are away, if they choose to write on Thursday, they can. If they want to postpone, that's fine too. And we'll test Friday.
I'll do it on Monday.